Okay, great. Thanks a lot, guys. Yeah, hopefully I will actually be there this afternoon, but so far that hasn't worked so effectively, so let's give it a shot. Before I kind of dive into talking about some of the data or the questions, I wanted to just get everybody on the same page with the particular sector of the Pollock fishery I'm going to talk about today, and that's the catcher vessel only sector, or the shoreside sector. It accounts for about half of the quota for the Bering Sea Pollock fleet. So these vessels are doing shoreside deliveries only, the majority of which are going to Dutch and Akutan. We've got about 90 vessels ranging from 80 to 200 feet long, and they're making 2 to 5 day long trips typically. The fishery is split into two seasons, which is the winter A season and the summer B season. Most of what I'll talk about today is the summer B season, but hopefully I'll remember to actually point that out when it's relevant. So the particular questions that we're interested in, especially with the context of this conference, is first, are fleet behaviors related to the dynamics of the Bering Sea region? For example, do vessels fish in different places during warm and cold years? And then secondarily, if that's the case, if they do respond to these behaviors, is everybody equally resilient to these dynamics? Do large and small boats respond the same, for example? Is everybody equally able to adapt? So in order to answer this question, we needed to reconstruct fishing trips so that we could kind of track the dynamics of how boats were moving over time, and then see if those movements were related to any of the particular characteristics of the Bering that we could keep track of. So we took data from 2003 to 2014, and using vessel monitoring system, or VMS data, we had the location of every boat every 30 minutes for the duration of the data period. And with that, we were able to reconstruct where vessels went and how long each trip was, how far they traveled. So we could take the travel distances and durations and link those then to the fish ticket data, which provided us with catch landings data and gross earnings for Pollock. In recent years, the Amendment 91 economic data reports have done surveys of the Pollock boats so that we actually have fuel consumption data for when they're transiting and when they're fishing. And using this, we could take then the gross earnings from fish tickets and convert those into net earnings and get a sense of some of the costs of the trips. And in the end, we ended up with more than 23,000 Pollock trips to analyze, which had a gross ex-vessel value of around $2 billion. So a pretty substantial scale of data we're looking at here. Some of the different drivers that we looked at included water temperature and the size of the cold pool in a given year, the Pollock abundance, TAC, or total allowable catch, extent of the sea ice, fuel, fishing costs, bycatch, mostly salmon we looked at, and then fish price. It ended up that of all these, the water temperature and Pollock abundance, those top 2 points ended up being the most significant, and so those are the ones we'll look at today. So the top slide here shows the Pollock abundance from 2003 to 2014, and the horizontal dashed line in both of these figures shows the average during this period. So you'll see that during the early years, 2003 to 2005, Pollock stocks were above average in terms of abundance. And then in those mid-2000 times, so 2006 to 2010, they were below average before coming back up in the 20 teens. And in the bottom plot, you see the bottom temperature anomaly, which you see those the 2003, 4, 5, the so-called warm years that everybody talks about in the Bering Sea. Before then, in the mid-2000s, it's dropping below average temperatures and bouncing around a little bit subsequently. Some of you may be wondering why I don't have the warm blob era 14, 15, 16 all represented here. And that's because we don't have the fish ticket economic data. They're not available yet. So for the point of today, I'm just leaving those out so that we can kind of complete the picture with the data that we have. So how would we expect the Pollock abundance, the climate, and the fleet to kind of interplay with each other? How would we expect them to respond? And it's pretty well known that fish move in response to the cold pool. So Pollock, despite being supposedly cold water fish, they don't seem to like cold water that much. So they tend to move in response to where the cold pool is. You'd think that they would want to move to California, but instead they just move away from the cold pool. some modeling work by Franz Mueller et al. Has shown that warmer waters are expected to yield lower pollock recruitment. And so if we have lower recruitment and fish moving in response to the cold pool, it may turn out that the preferred fishing grounds, which are closer to port, end up yielding lower catches. If this happens, then vessels are faced with a number of decisions about how to respond to that. So if you have to respond to fish movement or abundance changes, you could have a dramatic change and change your business model altogether. You could trade or sell your quota, you could target differently, you could, to a very limited extent, you may be able to charter for surveys, you may be able to tender for salmon fisheries, or a few vessels have contracts to catch quota from other ships. More likely, you can change your daily fishing model, which would be a less dramatic change. And so you could target smaller fish, or you could travel farther trying to find where the fish are. And this last point is the one I'm going to focus on for the rest of the time period. So on the y-axis here, so you should be looking at a number of different histograms here. So on the y-axis, this is the distance traveled for each trip during the time periods. The red histograms or density curves are A season, and you'll notice that aside from a little bit of shape difference, they're pretty much the same from year to year. The blue histograms are B season, and you'll notice that especially starting around 2006 up through 2010, you end up with some kind of a bimodal characteristic of these data as you start to see a greater proportion of trips that are longer happening. You should now be seeing a vertical white line overlain on each of these figures. And this line, it took me a little while to figure out where to put it, but this ends up being at 700 miles. And so this is what I've defined as the cutoff or the threshold for a long trip. So in 2006, 7, 8, 9, 10 especially, you see a lot more of these long trips during B season. Another way we can look at that is by saying, okay, what proportion of the trips in a given year were long? And so I've converted this proportion to an anomaly, which will become clear why I did that in a second. But again, the horizontal dashed line is the average, and you'll see that in 2003, 4, 5, the warm years in the Bering Sea, we had a below average proportion of trips that were long. And then in the mid-2000s here, we see a much higher proportion of trips that ended up being long. That highest point at 2008 there, it ends up being about 40% of the trips were long trips. And this now may be the best correlation I will have in my entire scientific career. You should see the proportion of trips that were long is still there. That's the solid line. And then you should now see a dashed line with the label bottom temperature. And this is showing now how the bottom temperature and the proportion of trips that were long are related to each other. And it ends up being a correlation of about a 0.92 or 0.93, suggesting that there's a pretty strong relationship between the bottom temperature and the proportion of trips that are long in a given year. Similarly, the pollock abundance ends up with almost as strong of a correlation. It ends up being about a 0.89, 0.9. And again, it almost looks like a mirror image of this proportion of trips that are long figure. So vessel behavior, B-season vessel behaviors, relate to the variability in the Bering Sea environment. That's shown pretty strongly here. But the question that becomes, are these long trips worth it? Is this a useful strategy for hedging against changes in the environment? The y-axis now is catch per unit effort. So this is pounds of fish per time. And you'll see now that the red figures now, the red histograms are short trips, and the blue are long trips. And you'll notice that in almost every case where there were years with a lot of long trips, the long trip is shifted farther to the right, meaning that there is a larger catch per unit effort or a higher catch rate among the trips that traveled far, which you would hope that if you're going to travel far, you're going to end up having higher catch rates. So it ends up, that's good, we would expect that. It also makes sense because if you're going to travel farther, you're not going to have as much time that you can spend fishing. So these trips are constrained by the freshness of the fish. So if you travel farther to catch your fish, it doesn't mean that you can simply stay out at sea longer. It means that you need to be more efficient with your fishing because you still have to get the fish back to port with about the same amount of time since they were first caught. So you really do need to be in areas where the catch rates are higher. So most of the vessels, it turns out, that are making the long trips are the larger vessels, and there ends up being a strong relationship between vessel size and the proportion of trips that are long. So we end up seeing that larger vessels are more likely to buffer against lower catch rates by traveling farther in search of better fishing, so they can go to better fishing grounds. But it turns out that they're not making a lot more money by doing this, but they're sustaining their net revenues. So now this is a similar plot to the last one, but on the y-axis, instead of catch per unit effort, we're looking at net earnings per trip day. So I've factored in fuel cost here, and we're looking at earnings per time, or an earnings rate, essentially. And what you should notice is that the long trips, the blue, and the short trips, the red, are almost perfectly overlain on top of each other in each of the years now, and there ends up being no statistical difference between the short trips and the long trips in terms of earnings per day. So it looks like these longer vessels, or the larger vessels, the longer trips, are finding higher catch rates, and in doing so, they're essentially just sustaining the revenues that they would have hoped to have had in a good short trip. So in sustaining their net revenues per trip day, vessels that made long trips did, however, reduce the variability in their revenue. So they were able to make a longer trip in order to buffer against changes in their revenue. So, of course, you wouldn't want to show up to work one day and not know exactly what wage you're going to work, right, or earn. So the less variability you have in your income, the better off you're going to be. So now, if we try to look at that on a per-vessel basis, now the x-axis in this figure is the proportion of trips that were long, and the y-axis here is the variability of your annual B-season revenues. So the points in the plot, each one represents a different vessel, and this is the mean variability of their revenue. And the bars, the error bars, are one standard deviation. You'll notice that towards the left side of the plot, the points are primarily above this white line, which is just a reference line. And as you increase the proportion of trips that were long, more and more of those trips are below that line, and they have higher standard deviations. So essentially what you're seeing is that the fewer long trips you made, the more variable your revenue was. And I should note, in case anybody is wondering about proprietary data, I've removed a number of vessels from this plot so that there's no way you could identify an individual vessel here. And by not labeling the y-axis, I've also removed any way of kind of quantifying an individual vessel's data. So kind of putting all this together, we see that B-season behaviors are strongly correlated with pollock abundance and with bottom temperature. However, it's a little bit difficult to tease out the interrelationship, the relationship between the bottom temperature and the abundance, especially because we haven't had any warm, low abundance years. So we've had cold years that had both high and low abundance, and we've had warm years with high abundance, but we haven't had any warm years with low abundance yet. The next point, vessels with fewer long trips, which are mostly the smaller vessels, had more variable revenue, suggesting that they're less resilient to current kind of changes or dynamics. They're less able to buffer against some of the changes. Longer trips stabilized revenues when the catch rates close to port were slower. So if fishing near port wasn't as good, longer trips enabled you to maintain your revenue. However, the larger vessels can make longer trips, but they require larger catches in order to make it cost-effective. And it seems that right now they're already kind of operating towards the edge of this margin. The longer trips aren't earning them much more money. So if the dynamics, the environmental dynamics actually get worse or stronger, these larger vessels may have less buffering capacity. And being larger vessels, they're a little bit more married to being pollock specialists, so less versatility. And next slide, and I think I'm out of time, but if there's any comments or questions.
Thanks a lot, Jordan. Appreciate you taking the time to dial in remote.